Yeah, I can hear myself talking. Great. So thank you so much for the introduction, Tyler. It's weird to have someone talk about me that's not myself for once. I like it. But anyway, my name's Matherne. I'm a rock licker, apparently. I study geology over at LSU, specifically planetary science, but I won't be talking about any of that. I'll be talking instead about astrophotography. And essentially that is a fancy word to make us feel better about ourselves, which is just we take pictures of the stars and galaxies and stuff and make them look prettier. So for example, this is a picture of the Andromeda Galaxy. It's not working, I'm sorry. I don't know what's going on.
I don't know either. You're good. Why isn't it working?
Is that the wrong one? That's the wrong one.
It's okay. We'll fix it. Just keep going for now.
Okay, so anyway, flashback 5 years from now, how I got started in all this. Imagine me, about the same height I am now, maybe about 20 pounds lighter. I ate about 2 pieces of broccoli before I came here. Trying to get that 5-year figure back, but there's always tomorrow, I guess. So there we go. 5 years ago, Drew Hastings posted this picture of what is known as the Lagoon Nebula on an internet website that I happened to stumble across. And my first reaction was, geez, wow, that's an awesome picture that was taken by the Hubble telescope or NASA. I didn't really know. I was like, a cool picture though. So I was like, I want to learn more about this target specifically. So I was reading comments, trying to find out what it is, how it was taken, and I came across a long comment by Drew himself that essentially started talking about things like equipment, filters, exposure time, processing, and I was kind of making the connection that, hey, maybe this wasn't taken by NASA, this guy actually took it, which led me to a long rabbit hole of looking at a lot of pictures taken by other people, as well as looking at the sort of equipment you need to do this, as well as the actual picture taken by NASA, and to sort of orient you as to what we're looking at. Here is the NASA image, and here in this bright core is essentially where the Hubble is pointing. So you can't really see exactly what it is, but if you use your imagination, you can sort of fill in the details. But this is the first ever astrophoto I ever took. For those of you in the back, it's like 8 pixels big. It's Saturn, I promise. But so I took it with my brother's telescope that I stole from him. I borrowed, sorry Clay. I borrowed it. I took it out to the front yard and held my cell phone up to the eyepiece. And I was very excited with the results. I couldn't, A, believe that I had Saturn. I had never seen a planet through a telescope before. And I was also kind of blown away that the first bright thing I pointed to in the sky was a planet. But through a lot of new equipment, a lot of practice, I was able to move away from Saturn and sort of complete the whole entire solar system. So we have the Sun, Mercury, Venus, the Moon, Mars, Jupiter, new Saturn, Uranus, and Neptune, and a TIE fighter, also known as the International Space Station. I tweeted at them to say cheese, but they never retweeted me back, so I don't know what they did. Outside of that, we also have pictures of the Milky Way. This was taken out in Colorado Springs with a few of my friends. We were doing field work out there. They actually came tonight. Thank you so much, guys. But this is actually one of my favorite pictures I've ever taken. Mainly because A, I like the way it looks, but B, just because A, they had never seen the Milky Way before, and that's sort of what I enjoy most about astrophotography, is just how it allows anyone, scientist or not, to sort of connect with astronomy and space in order to just through pictures. Like, you don't have to understand math, you don't have to understand science. It's just creating pretty pictures, essentially. Other than that, I've also began taking pictures of galaxies. For example, here's a picture of the Whirlpool Galaxy. I'm quite fond of it, mainly because unlike most pictures, or unlike most galaxies and nebulas, it actually looks like its name. Most galaxies have weird names, like Penguin Galaxy. No galaxy looks like a penguin. Other than that, here's also the Horsehead and the Flame Nebula. Again, more galaxies and nebulas that actually look like their name implies. But here we go. Here's sort of what we were starting off with, just sort of a telescope and taking pictures of the moon right here in Baton Rouge. This was not the telescope I stole from my brother. This is about 4 years ago, though. My brother still managed to pay me back for stealing his telescope by jumping up and down and knocking my camera out of focus for this like 30 seconds right after I took this picture. But this is sort of what we would do in Baton Rouge. There's a lot of light pollution, so you're kind of limited in terms of what you can do. But this is what we had. It's not anything super special, just a normal 8-inch telescope, and it has a little $100 webcam attached to it. Other than that, here we have the Milky Way. I took that about 30 minutes outside of Baton Rouge, near the Atchafalaya Wildlife Refuge. Probably the darkest sights you can get, as far as I know, in this area. That was taken underneath an overpass, actually. So if there's any like serial killers in the audience, I go out there alone. Really, please don't kill me. I really like the location, and I do get scared because I don't bring anyone else. Here we go. Here's me taking pictures of deep sky stuff. What I like about this is actually that it was freezing that night, so you can see sort of icicles forming on the blades of grass, and a space heater, not to keep me warm, but to keep the telescope warm, because essentially ice was forming on it at this point. So I had to point a space heater at it to keep it a few degrees above freezing. Fast forward to today, though, and essentially I've at this point been picked up by an observatory who offers me all of their equipment. It's sort of an amateur observatory, so it's filled with all amateur equipment, things that you can buy. It's nothing scientific grade, but it's something they offer to the public. And they essentially hired me in order to make pretty pictures for them, which is great for my sleep schedule and my grades, personally. I'm not an insomniac anymore. But I do really enjoy it. It's out in New Mexico, so I also get to deal with some really dark skies, things that we don't have here in Baton Rouge, some really clear skies with really good seeing, no light pollution. But here's what a general astrophotography setup looks like. You have a mount, which is this black tripod, and essentially what it does is it rotates with the sky, because the sky rotates throughout the night, and you need to keep up with it. On top of that, we have a telescope with a camera attached to it, with this thing called a T-adapter highlighted in green. And essentially all that is letting you use your telescope as a big telephoto lens, essentially. And then on top of that telescope, you have a smaller telescope and a smaller camera. And that's a fancy thing we like to call guiding, which is where you have a little camera, look at the sky, it feeds back to the mount exactly how the sky is moving, and it makes slight adjustments just to give you a little bit more accurate tracking. But the reason we need this, and there we go. So here's an animation. I made a time lapse. It was like 9 hours long, I think, of footage. This is the 2015 Perseid meteor shower. So you can actually pick up a few meteors if you look closely, but since it's so much time compressed in such a short time, they only show up per frame, so you gotta be quick. But as you can see, the stars are rotating throughout the night. And if you were to point your telescope at any point in the sky and let your camera expose, so just for reference, I'll normally expose for 10 to 30 minutes per image. However, in this case, if you were to expose for even as little as 2, maybe 3 seconds, you would end up with an image that had trailing if you didn't have a mount to track the stars as they went across the sky. And here's actually what it ended up at the end of the night. This is the version that didn't have the time lapse. You can see a few meteors here, there. They showed up. I didn't use the whole 9 hours of footage for this image. I just used a few hours. Here's why we need this, though, because there is something known as the signal-to-noise ratio, and it's how much noise your camera generates whenever you're taking a picture of something so faint you need a lot of signal, also the photons, which are coming in from the galaxy, hitting your sensor in order to create a usable image. So this animation was made by a friend of mine, and essentially is showing that difference in exposure time as you go through it. So each frame within this animation is essentially a quadrupling of exposure time. So when you start off, and it's just that a lot of noise with that thing that might be something faint and fuzzy in the center that you wouldn't know really existed if you didn't see the final image, that's 1 minute. The next frame is 4 minutes, 16 minutes, 64 minutes, 256, 1,024. I think I memorized that right. I'm not very good at math. I lick rocks, come on. But the final image, you can see there is a noticeable galaxy in the center of it, and the noise is pretty much subdued. You can really see the galaxy, noise is gone, and that is known as the pinwheel galaxy. But as you can see, there is an acquisition portion of this, but there's also a processing portion. So after you have all of these photons hit your sensor, what do? So here, there's a pretty big misconception out there that a lot of astrophotographers sort of paint detail in or add things that aren't there. Not really true at all, actually. If an amateur astrophotographer did that, I feel like he'd be ostracized by the community rather quickly. I mean, we're pretty small, and if someone is painting in things, we wouldn't really be cool with that. But this is generally what we're doing, is we're taking the image, and we're essentially highlighting all of the things that our cameras have captured. We're not adding anything, we're just changing things to make them more visually appealing or more true to what they are actually like. And I think this is an animation that needs to play. There we go. So I did have a little demonstration plan for this, but it's a whole thing. I'm not going to go into it. But we have your differences between visual light, you have your differences between true color, and you have false color. Now on the surface, you might think visual and true color, they sound the same. What could the difference be? So if I was standing up here, and suddenly, like for example, what color would my pants be? Anyone? Gray, sure. Gray, blue, yeah, I'll take that. It's not a trick question. However, if the lights were cut off, now what color would my pants be? There's essentially, yeah, I'm hearing mixed answers now. So you can either stick with your original answer, gray, blue, navy, whatever it may be, or suddenly they're black. What is it? So this is sort of the issue we deal with in astronomy, where we have images like this, where you look at them through the telescope and they're so faint, they look gray. And that's because our eyes aren't good at detecting color when something is very dim. If something is very bright, like this light shining on me right now, you can suddenly tell what color things are. So we use known star databases, like we know what color stars are, and we can use those to color calibrate our images in order to end up with something that is color accurate by the end of it. Now for false color, that all goes out the window. We just kind of are highlighting compositional differences in nebula, because as you can see, the true color is all red. And then the false color, though, we can actually see the elemental differences, like the orange is hydrogen and the blue is oxygen. I'm not going to go into too much of that, though. And outside of that, though, there is editing that is strictly eye candy and not scientific whatsoever. For example, here are two little pseudo time lapses I made, one of the Andromeda Galaxy, one of the Triangulum Galaxy, in which we sort of see how these might spin throughout millions of years. These are created from still images, not videos, not actual time lapses or any actual data, to show just how unscientific they are. The first one I made right here, I had it spinning the wrong way when I first made it. So again, don't ever like cite these on the paper. Don't do that, no, wrong. But it's not just amateur astrophotographers that deal with this sort of thing. This is something that NASA deals with as well. For example, this is an image of the Sombrero Galaxy, really popular. I think it was the standard desktop on like a Mac like 6 or 7 years ago. It was one of the first images of space that I really enjoyed, and at the time, I thought it was like CGI or made up or whatever it may be. This is actually entirely in the visible spectrum and not a CGI image at all. Moving over, though, we actually have some infrared data. This is no longer in the visible spectrum. However, this data does have use in that we have that cloud of dust and stars highlighted within the Sombrero Galaxy, noted by that red band, which we couldn't see in the visual spectrum. We knew that difference was there, but as you can see, it's really stark. Like, it's almost like two galaxies in one. I actually saw an article with that title. It's not true, it's clickbait, but it existed. It's just one galaxy with pretty different properties throughout it. Weird. Also, we have Chandra X-ray data, again, entirely outside the visual spectrum, but it tells us something we didn't know. Here's another example of astronomy exciting people. This is probably one of Hubble's most famous images, known as the Pillars of Creation. It was taken decades ago. This is the original one. But for the anniversary, they ended up taking it again. Here's the new version they took, I think a year or two ago. I'm not quite sure on the dates. But this is the new one they ended up with. And I saw articles all over the place for this. Any major news article had picked up a story on Hubble taking this new image. And I was just, it was nice to see all these sorts of new things coming out from this, this new image. Same thing goes for this, Andromeda. We have increasing sort of resolution throughout the image, where we have a closeness view of it. This is the largest mosaic Hubble ever took, up until a few years ago, actually. With that little green pixel right there being that last square over there. It's kind of hard to forget that these things are clouds of stars and not just clouds floating out in space. Here's another one now, ultra deep field again. Hundreds of thousand galaxies in this images. Just 2 stars right there, though, are the only ones that lie within our Milky Way. Everything else is a galaxy. But at this time, I would like to take any questions you have for me. I know Tyler will have one, of course. But I'd like to thank you all for your time. Thank you for coming out. Thank you so much.
All right, what a fantastic talk. Yes, and we slightly cheated. He kind of knows what I'm going to ask. Okay, so with those animations you were showing, what sort of techniques are being applied there? Is it just pure black magic, or are we talking like machine learning? What's happening?
Okay, so the animations, you're referring to the animations with the galaxies. All the other animations were real. The only fake pseudo animations were the ones with the galaxy spinning. And they are what is known as plotographs. There's another thing known as cinemagraphs that some of you may have heard of, which is where someone takes a video and makes like a nice looping animation out of it. Plotographs were developed in order to take still images and make a nice looping animation out of, where you mask off certain areas and you draw some arrows, and essentially it drags pixels along at different rates that you specify in order to create a sort of pseudo animation to whatever you want, essentially. That's what that is. So nothing super scientific. You can download a lot of apps on your phone that do this, not just with galaxies. I've seen people do it with sunset images before, it looks nice. I've seen a lot of my friends do it with nebulas before, that looks nice. But there's a lot of different things that you can do with plotographs that just look great.
Yes, here. How much money have you spent on equipment?
So personally, thousands. But luckily, I was able to get rid of it, a lot of it. A lot of the stuff I have now, I use solely for outreach, because what I enjoy the most is getting the public excited about astronomy, which is why I'm giving this talk now, which is why I do what I do. So I have a large telescope that I use for outreach events, like with the Baton Rouge Astronomical Society. Outside of that, though, I don't really use any deep space photography stuff, but the observatory I work for, I have access to hundreds of thousands of dollars worth of equipment, more than I would ever be able to afford on my LSU stipend. Please pay me more. Yes?
So are you taking long exposures, or are you taking multiple short exposures and stacking them? Can you explain why you do either one?
Okay, that's a great question. Yeah, so it's both, actually. It depends on what you're taking a picture of. For the case of galaxies and nebulas, I take a lot of 10 to 30 minute exposures, and then combine them for an overall exposure upwards of 20 to 30 hours. The main difference between the two is they would both have the same signal-to-noise ratio, like one 30-hour exposure and a bunch of 30-minute exposures that equals 30 hour. 30 hours. However, one, you can't expose for 30 hours because you have the sun you have to worry about. But also, if something goes wrong, like you have a plane fly by, you have a satellite fly by, someone kicks your telescope mount or jumps up on the porch next to you, Clay, I'm not angry still. Those will mess up your exposures, and then you have to restart all over. So it's sort of a fail-safe to take a lot of the shorter ones and then combine them later. Yes?
I really liked that picture of your group standing and looking at the galaxy. How long did you have to expose for to get that pretty?
So the question was, how long did I have to expose for the Milky Way image of us underneath the Milky Way in Colorado Springs? That one in particular was a combination of 15 60-second exposures that I took. Normally when you're imaging the Milky Way, if you don't have a mount that tracks the sky, you're limited to around 15 to 20 seconds before you'll get star trails. However, I upset my my boss by bringing a tracking mount out there. They're like, that's stuff you don't need. And I was like, oh well, it's here now. So I did abuse it, and I did get to use it out there, which was a great thing. Ashley again. I did, so we only had to stand there for one of the images. So at the end, whenever we had the 15, 60-second exposures of the sky, since the Earth is rotating, the ground was entirely blurred. So I ended up taking one shot of us for 60 seconds where I turned off the tracking mount. So the stars in it are completely blurred. However, us standing there and underneath them is completely stable. And then I just merged the two once we were done. So the blue rings in the time lapse of the meteor shower image, the blue rings are stars and their movement throughout the night. Normally they wouldn't all be blue. As you notice in the time lapse, it was more of a yellow color. There's a fella named Roger Clark out there who's another fellow planetary scientist who has done a lot of work on keeping true color images of the night sky out there, because a lot of people, like myself, tend to make them more blue. So if it was a true color, they wouldn't all be blue. There'd be shades of yellow in there and shades of blue. But in general, those rings themselves are just stars and their movement over the course of 4-ish hours. Yes?
So I see you're a Redditor. What's your favorite follow for getting more information?
So I am a Redditor, yes. Please don't find me. I have a very embarrassing account name. I should probably change that. Anyway, pages to follow, I would suggest the Space is a default one that's great. There is one called Astrophotography, which a whole bunch of amateurs contribute their work to. I have a lot of friends that post there. But then there's also the Astronomy subreddit. That's another great one as well.
Anyway, so yeah, I'm here to talk a little bit about, and I'm just trying to measure the stage in the dark so I don't accidentally walk right off of it. Okay. So the title of my talk is Exoplanets from Infancy to Maturity. What I'm showing here is it's kind of an evolutionary sequence. So we have a protoplanetary disk here that's full of gas. Gas giants are probably forming in this stage. Eventually the gas from a disk like this clears and becomes a debris disk, which is being imaged here. Here it's just dust we're seeing. Eventually the dust clears, we see young, hot protoplanets in a system like this, and then finally you might end up with a planet around a star. Each of these systems has their own interesting story, but I'm just going to focus on one small aspect of this for this talk. So, to start with, I looked up today. According to NASA Exoplanet Archive, we have discovered 3,912 exoplanets today, which is, getting closer and closer to 4,000. So an exoplanet is just a planet around another star. So our star has 8 planets, right? 8, yes, 8. But there are a lot, thousands of billions of stars in our galaxy, and we expect that most of them have one or more planets around them, and so we call them exoplanets to distinguish them from planets in our own solar system. And what I'm showing here is a plot of the mass of the planet versus the period. And so for reference, Earth is this yellow star down here. Jupiter is up here in green, and Saturn is there in blue. And these are the detections we have to date. And so there's some interesting patterns in terms of what detection methods are more efficient at detecting what kinds of planets in terms of their masses and periods. And I just want to point out a couple interesting groups. So there's a clump here of what we call hot Jupiters, because they're about a Jupiter mass, more or less, but they're on these orbits that are just a few days, right? So they're whipping around their star in a few days. And so these orbits are, well interior to where Mercury's orbit is around our star. So if 1 AU is Earth's sun distance, these planets are like 5% that distance. And then also, there's also a collection of very distant planets, and so these are on orbits of millions of days. So these are, far beyond like Pluto's orbit, thousands of AU as opposed to just a few AU. And so, so the question is, like, where do these different planet populations come from? How do we get these planets that are so different from what we see in our own solar system, right? We have Earth, Jupiter, and Saturn, and we see all these systems that are completely unlike our own solar system. And our own solar system is shown here, and so we can look at the orbits. They appear to be mostly coplanar, so if we were to look at sort of an edge-on view of the solar system, all the planets, Pluto is not a planet, right? It is a Kuiper belt object. The planets in our solar system are nicely behaved. They're on these nice circular orbits, and they're mostly all in the same plane. So let's talk about Pluto for a little bit, because Pluto is the first of the Kuiper belt objects that were ever to be discovered. And then as we discovered more and more of them, we realized that Pluto is just one of the largest of this population of objects out there. And so there was a planet for some time between Mars and Jupiter called Ceres, but nobody has heard of Ceres anymore because it's just one of the largest asteroids now, right? And so as our understanding of the solar system changes, we change the categorizations of these. So that doesn't mean that Pluto isn't interesting. Pluto is a very interesting object, but it is not a planet. Anyway, let's talk about exoplanets. So the first exoplanet to be discovered is 51 Peg B. And what I'm going to do is I'm going to sketch on here 51 Peg B's orbit. Oh, and just to note, so this inner solar system all fits in within this tiny little circle within the outer solar system. And again, there's a zoom in here for the inner solar system and the outer solar system. And so you got to watch carefully as I animate this. Right, 51 Peg B's orbit is 0.5 AU. And so if I draw the orbit on here, it's basically the same size as the circle that they drew for the sun, right? So if I were to go back, there's the sun, right? And then you draw on the orbit. That's how small the orbit is. And that's why these hot Jupiters are so interesting, because we see nothing like that in our own solar system. And we, part of the reason why this discovery of 51 Peg B was so interesting was not just a planet outside our solar system, but because it is so different from what we already know. So here's some examples of some of these cold Jupiter planets. This is the HR 8799 system. You can see 1, 2, 3, 4 planets in the system. And so this is, we're actually observing, here's the date of these observations and time down here. And so they start in 2010 and go up through 2015 or so. So over those 6 years, we can actually watch these planets move around the central star. I should note that there are very special post-processing techniques to subtract the starlight. If we were to leave the star in here, it would wash out the signals of these planets. And so that's why there's this dark circle in here, because of the techniques used to subtract the starlight. You basically just stick a black circle on there to basically, it's essentially drawn in there. So the star is there, but we don't actually see it in these images. And so the interesting thing about this system is if I were to draw the orbits of our outer solar system planets on here, first the masses of these planets are quite large. So we estimate their masses to be up to about 10 times Jupiter's mass. And if I were to draw in the orbits of our solar system, there's Jupiter and then Saturn, Uranus, and Neptune. So they're planets much larger than Jupiter, but on these expanded orbits, larger than we see in our own solar system. Okay, so, and TRAPPIST-1 is a particularly interesting system. So this is a multi-planet system. We have 1, 2, 3, 4, 5, 6, 7 dwarf planets around a dwarf star. So it's kind of a Snow White system. And then here's our inner solar system, right? Mercury, Venus, Earth, Mars. If we were to draw the TRAPPIST system to scale on our solar system, it would all fit in the sketch there. So it's a very compact system. And so, this begs the question, where are these planets actually forming? Because we have, we thought we understood planet formation in our own solar system. But clearly something else is happening in these other solar systems. Do planets in those systems form in similar regions where they do in our solar system and then migrate? Are planets migrating? Is the solar system unique? Right? We like to think that there's this nice orderly progression of terrestrial type planets, rocky planets in the inner solar system and gas giants further out. But a lot of what we've seen has upended those theories. And so, if there aren't other solar systems like our own, what does that mean about habitability and life? So I like to approach this from the point of view that in order to understand these questions, we need to directly probe the planet formation era. And so this is just a cartoon diagram of our current understanding of how planets form. So you start out with giant molecular clouds in the galaxy. You have these overdense regions that are created because they're turbulent. And so because things are mixing around, you get some areas that are more concentrated than others. One of these overdense regions starts to collapse in on itself under its own gravity, not love. This is my first time in Louisiana, and you're booing me? Jeez. All right. You eventually have the formation of a protostar. You have continued infall of material onto the protostar. Eventually, the infall stops, or at least slows to a trickle. You have the formation of a protoplanetary disk. And then eventually the gas clears away, you're left with a debris disk, and the dust clears away, you're left with planets. And so we think planets are forming during these disk phases. And so this gas-rich disk phase is often referred to as a protoplanetary disk. The dusty phase is referred to as a debris disk. And I mostly study these protoplanetary disk phases. And I'll tell you a little bit about some of the work I'm doing to help us understand planet formation during that period. Okay, so I'm mostly a theorist. But what I work on is trying to interpret images of these protoplanetary disks, like some of these that have been taken of a number of different interesting young stars. And this is just from a review paper showing that we have disks. So again, you're using techniques to blot out the central star, and that's what's represented by these black circles in each of these images. And you can see that there's some hints of interesting spiral features, broken spiral arms here, some more spiral arms here, possibly a gap forming here. And so these particular images are all taken in scattered light imaging. So this is typically near-infrared light. You're looking at light that's emitted from the star, reflects off the surface of the disk, and that's what we're seeing. But you could also look at these disks in millimeter or submillimeter wave photons. And ALMA, the Atacama Large Millimeter Submillimeter Array, has kind of transformed this field because it's been so powerful in terms of imaging some of these disks. And this is just a picture of some of the telescopes in the array. So again, it's in the Atacama Desert, so it's a high, dry plateau, and there's this array of large telescopes. I like that this image has some trucks on here for scale, so you can get a sense of how big these telescopes are. And in the expanded configuration, the longest distance between one telescope and the other is about 32 kilometers. So it's quite an interesting instrument and very powerful. And so this is a recent paper by Andrews et al. Showing a suite of disks that have been imaged by ALMA. And I'm going to hopefully this, there we go. And so it's just scrolling through and showing you all these disk images that have been produced by ALMA on different systems. And you can see, I'm going to show this again because take note of the different features you see. No two disks look alike, and part of that is just due to orientation, right? So if you have a disk that's face on, it's going to look rounder than one that's closer to edge on. But in addition to that, you're seeing things like that might be spiral arms, a lot of ring-like structures, gap-like structures. There's clearly interesting stuff going on in these protoplanetary disks. And so what's causing those, right? And we all want them to be due to planets. And we need to be a little careful about that interpretation because, there are some other explanations for that, but we still really want to be able to find planets in there. So let's think about, if there are planets in these disks, what would those signatures look like, and do they match the features that we're seeing in these disks? And the analogy I like to make here is you have these images of disks. Some of them are kind of fuzzy, kind of grainy images. And, to a trained eye, though, you might be able to interpret structure of these disks and be able to detect interesting formation processes, not unlike we see in, let's say, biology. Okay, and so I'd like to focus the rest of this talk on just this one particular disk. It's got the great name of HD 163296. And so this is one of the images that was taken of this disk by ALMA. It's the wavelength is 1.3 millimeters. And so you can see that there are multiple gaps that appear to be in this disk at 50 AU, 80 AU, and 130 AU. And for reference, Pluto's orbit is like, what, 50 AU? So this is a very large disk. Pluto is kind of like the limit of the size of our solar system, right? And so this disk is quite large. And if those gaps are being caused by planets, it's got planets forming at these large distances. And how did those planets get there? Okay, and this is just that same image, but with a slightly different color scale. And so there's also been images taken of this disk in near infrared light, where again we're seeing light that's scattering off the surface, so this is more reflected light. And I just like this animation, so I'm going to see if I can show it again. Right, so you're seeing the ALMA image, and then the scattered light image. And one thing to notice, if you look carefully as I switch back between these images, is that those gaps don't necessarily line up, right? So if you look at this gap here, for instance, the gap in scattered light is almost, but not quite, lined up, right? So what's going on? Why are we seeing different things at different wavelengths? And I'm going to draw in here a little yellow circle to sort of outline this contour here, where it appears the gap is in the 1.2 micron image, and then comparing it with where it is in ALMA, there's a clear offset. Okay, so what's causing that? Well, so when you're imaging the surface of a disk, what you should imagine is that when you're looking in scattered light, you're looking into a bowl. This disk is flared, its surface is flared, and so you might think of it as kind of bowl-shaped. So when you tip it towards you, you're looking down into the bowl, right? And so this ellipse is no longer centered on where the center of the star is. Okay, and so this is a model that I've run for a gap in a disk. And so now if we model what we would see in this exact same disk at 1 millimeter, we see that same offset. See this yellow circle, this yellow ellipse is not quite aligned with the red ellipse there. I'm going to go back here. So this yellow ellipse is supposed to line up with that bright ring of emission. And here, where it's not aligned. And what we're seeing is that scattered light is showing us the surface of the disk. But when you're looking in the millimeter, it's almost like you're taking an X-ray of the disk. You're seeing through the disk. You're seeing dust at the midplane. And because you're seeing dust at the midplane, that's going to be more symmetric than what we see in the scattered light. Okay? And so if we compare this observation of HD 163296 with my model, it's oriented like this, right? And so, again, going back to here, remember this, so this is the near side. This bottom edge is the near side, the top edge is the far side. Okay, and so what we're seeing is that this disk is tipped so that the near side of the disk is on this side, and the far side is over there. And then the ALMA, again, you're seeing through the disk, and so it looks more axisymmetric. Okay, and that's basically the story I wanted to tell. There's a lot more instruments coming online. JWST is a telescope due to be launched in 2021. But if anybody reads XKCD, and you look at predicted launch dates versus time, there's a clear trend. And so Randall Munro is predicting late 2026. But anyway, there are more and greater telescopes that we can bring to bear to try to solve this problem. And hopefully we'll be able to answer some of the questions that I posed tonight. So, thank you. I'd actually rather answer questions, I think. Extraterrestrial life. People are actively studying habitability. And it's a very rich field. There's a lot of unknowns, right? Because you have one instance of life on a planet, that being what we see here. Right? And so, what are we going to look for if we're trying to look for life on other planets? Well, let's try to look for life like our own, right? Because that's when we know. So we might look for things like oxygen in the atmosphere. Something you might look for is a chemical disequilibrium, because we see, for instance, in our atmosphere the presence of both methane and oxygen, which, if it was in equilibrium, those molecular species would not exist simultaneously in chemical equilibrium. They would react. So there's a very rich field of people looking for what are called biosignatures, and there are telescopes like HABEX is a proposed mission that might be able to detect biosignatures on other planets. Trying to speculate about life unlike what we already know is very much a philosophical endeavor, and it's hard to pinpoint. It's hard to do work on that because you're entering this realm of philosophy to some extent. Right, so
if they are at different times, different angles, can they be aligned properly?
Right, so you're asking about the images I showed where you looked at in the millimeter wavelength and you looked in the infrared wavelengths. They look different. And yes, those were taken at different times, but we don't expect the disk to change significantly over that period of time. If you think about orbits, when you're looking at these, like 100 AU, they're very, very slow. So we don't expect the system to change very much. It's not going to suddenly tilt. So the changes in tilt that we're seeing are real. right? And it's because we're looking at different wavelengths, right? Just like if I were to look at you, in optical wavelengths, I'm seeing your surface. If I were to look at an X-ray of you, I'd see something completely different. So that's one way to think about what you're seeing when you look at these different wavelengths. If you look at 1 micron, you're seeing the surface of the disk. If you're looking at 1 millimeter, you're seeing through the disk, the interior of the disk. Right, so the question is, if we're proposing that planets are causing these gaps, can ALMA resolve these planets? And ALMA cannot resolve these planets. They're very, very small. But a large planet will create this large-scale feature. So something of roughly about Jupiter mass is enough to basically completely clear its orbital path on this disk. Right, and so what we think we're seeing are gas giant planets in the act of forming in these disks, clearing out these gaps. So that's what we're seeing in ALMA. So if we were to look at, let's see if we can go back. Right, so these disks, right, you see gaps in a number of these disks, and the spacing of those gaps can put a limit on the masses the planet's forming, but nowhere in there can you say there's definitively a planet in there, not at the resolution that ALMA currently has. And possibly not ever to some extent, because these planets, they're very, very small in size. And so any emission from the planet itself is going to be swamped by what we're seeing from the disk. So the question is about when might we be able to construct telescopes in space as opposed to on the ground. I don't really have the expertise to speak to that. I do know that all the missions that are currently being planned by NASA for astronomy are basically built on the ground and launched into space. So being able to build something in space is going to require a lot of infrastructure. And if we're talking about just astronomy, that's a small part of what's going on with, it's only one part of space exploration, I should say. So if we're going to launch things into space, I think there are, way more, there's certainly more telescopes in space looking down, let's say, than looking out into space, right? And so a lot of what's being driven in terms of launching things into orbit and putting spacecraft into space is driven, partly by NASA, but to a large extent also by military type stuff. And so, yeah, I can only speak to the missions that I know that are already planned for doing astrophysics in space.
All right, Tyler took the privilege of asking the first question for each of the speakers. So I'm going to ask the very first question for the panel guests, and that is, what is each of your favorite Pokemon?
Pikachu, because that's the only one I know.
I'm going to have to go with Ammonite because it's kind of a geologic fossil.
Quilava?
Jirachi. Rayquaza.
Jigglypuff.
Any questions from the audience?
Questions, anyone?
That's not a fair. That's not fair.
I have a question. The idea of looking at different wavelengths and considering the geometry of the problem and what wavelength you're looking at would be affected by the a really like simplistic thing, but like a very elegant like idea to have come up with? Is this the kind of thing that was somebody said much earlier and you found the paper and were like, I'm going to actually do that now that we have the technology, or was it a thing that you were like, nobody's ever thought of this before, how did nobody think of this?
So the question is, in terms of looking at different wavelengths, how that affects what we're seeing in terms of the shapes of these disks. I guess how did I go about doing that? I actually have to think back to this. I think I actually approached this from a naive theorist point of view, saying like, well, what does this look like if I tilt it at different angles? Oh, you see different changes in the shapes, as you tilt the disk. But as you say, if you think about it, like if you have a bowl and when you tilt it back and forth, it's it becomes relatively intuitive. But a lot of what science works that way sometimes. You're trying to look for something deep and meaningful, and you realize, oh, this is actually something that we can see analogous to what we see in everyday life, and that making that connection, especially when you're doing stuff in astronomy, because these are never objects. I can never like go out and touch a disk and tilt it in different ways so that I can examine it differently. But that's just kind of the nature of how science works sometimes. Is you look at one thing and you realize, oh, actually, this is simpler than I thought it was going to be. How do you measure the mass of exoplanets, and how certain are you? So there's lots of different ways to measure planet masses. The most accurate would be doing what's called radial velocity measurements, where you're actually measuring the Doppler shift of the star as it's being tugged on by the planet. The ones I showed in the image where you saw the planets rotating, those are very model dependent. So what we had to do was make a model for what we thought the planet's temperature would be and their size, and how old they were. And so those models are very uncertain. There's no direct mass measurement there. It's all based on, well, what kind of an object and how old it would be to be emitting light like that.
So I haven't personally seen the Wyoming sky before. Sorry, the question was, how does the Wyoming sky compare to that Rouge sky? There's actually a great website out there called Dark Sight Finder, which will give you a map of the entire world and give you an associated what's known as a Bortle number, which is a measure of light pollution. So the area that I went to that was outside of Baton Rouge, about 35 minutes, is what's known as a Bortle 4, which is sort of the rural boundary is what they call it, I guess. Outside of that, though, I've seen some areas out in Colorado, which are Bortle 3, 2-ish. And those areas are a lot darker. You can see the Milky Way with your own naked eye. It appears to be a cloud of stars spanning across the sky with no real light pollution domes on the horizon. Personally, again, I've never been out in Wyoming, but given its location, I can assume a lot of the areas out there are similar in terms of light pollution. The only issue being is the farther up north you get, the less of the Milky Way core you can see. So I tend to try to stay as far south as I can in order to see as much of the Milky Way as I can, at least the core of it. Yes?
Who's your favorite woman in astronomy, and why is it Jocelyn Bell Burnell?
Wait, can you repeat the question?
Who's your favorite? Yeah, they'll repeat it. Repeat the question.
Who was that for?
All of you.
So the question was, who's your favorite woman in astronomy, and why is it not Jocelyn Bell? Why is it Jocelyn Bell Burnell? Well, see, my favorite woman in astronomy is actually Vera Rubin, because I had the chance to work at the same institution with her. So she discovered dark matter, and she worked down the hall from me when I was a postdoc. And she's one of the nicest people I've ever met, but also tough as nails. She would tell these stories about going to the observatory and being barred from things for being a woman. And so, you know, she's my personal hero. She passed away 2017, I believe, unfortunately. But so, yeah, she's my favorite.
So my favorite is actually, for similar reasons, I would say Tabby, just because her views sort of align with my own in that we're getting people excited about astronomy. I don't know how many of you have seen it, but Tabby runs her own Twitter page for her star, which she updates exciting news about it. I've seen it. I get excited about it. I know other people feel the same way. So any scientist, woman who excites the public about astronomy or anything to do with space in general is personally someone I look up to.
I currently cannot remember her name, but it's the woman, there's a photo of her, it's standing next to the stack of computer code she wrote by hand for the somebody might remember it eventually and tell me, but everybody knows this photo.
Mommy.
I'm not sure what to say right now. Why is it Jocelyn Bell Burnell? If you have not heard this story, this woman did not win the Nobel Prize for the discovery of pulsars. Her advisor did back, 30, 40 years ago. But it never really let her down, and she has like the most badass sense of just like awesomeness. In every single story, I've never met her myself, but every single story that I've read of her, I just love every single quote because she's just like, she doesn't care, right? She's just like, well, science is awesome and that's the way things are, and if you don't win the Nobel Prize, then you just get like 10 more other even more awesome prizes. Which is what happened when she won the Breakthrough Prize this past year, which was a whole lot more money, if I remember correctly, and a lot more notable than the Nobel Prize, which is proven to be sexist for the past 100 years, because only 3 women have won it over that time period. So, so that's why Jocelyn Bell Burnell is super freaking awesome. I'm just gonna leave it at that. And anyone want to add something else for Jocelyn Bell Burnell? Like how awesome she is. Okay. Any other questions? Yes. The question was, what is the best way to see the core of the Milky Way?
So, yeah, go to the southern hemisphere is great. We're actually moving our observatory to the Atacama Desert, which would be great. But if you're in Baton Rouge, I would say if your goal is to see the Milky Way and you've never seen it before, I would take, is it I-12, I-10, essentially towards Lafayette, I forget which one it is. But halfway through, you're on that really long bridge with no exits, and then you get to the first exit called the Whiskey Bay exit. Take it, sit under the overpass like me, hope you don't get murdered, boom. You can actually see the Milky Way if you look towards the south during the spring and summertime. During the winter, like it is now, you'd have to wait till really, really early in the morning and look towards the southeast, because it rises in the east, sets in the west. But as you progress through the year, it sort of changes when it rises and sets. Best times are spring and summer. Right now, it's not really up. You can see Orion, which is great, but if you're looking for the core of the Milky Way, it'll really only be up during the spring and summertime. Yes?
How is it that planets with a similar mass to Jupiter will form at different locations and temperatures?
So the question is, how do planets the mass of Jupiter form in different locations? This is a good question because our understanding of our solar system is that, well, if you get too close to the sun, like, you know, it gets too hot to form Jupiter, but if you get too far out, there's not enough mass, right? So that explains our solar system. There are also theories called migration, where these planets form in the same region where our Jupiter formed, but they somehow move either inward or outward. And so the problem with the theories that cause planets to migrate inward is they're hard to stop. So the question there becomes, well, if these mechanisms are operating, how do you end up with Jupiter where Jupiter is and not all these gas giants being in at least 3-day period orbits? Getting planets further out is harder, but then again, you see these disks that have quite large extents, so maybe they are large enough that there's still enough mass out of those wide distances for these planets to form. Another idea is maybe there's scattering going on. Maybe you have multiple Jupiter mass planets forming close together, and they gravitationally interact with each other, and one gets scattered further out. So those are some ideas anyway.
A related question, if you have multiple Jupiter mass planets within the diameter of our inner solar system, do you expect that to be a younger solar system? Do you expect collisions between those planets?
So the question is, if you have multiple Jupiter-sized planets in sort of like the region of our inner solar system, so like maybe within like 2 or 3 AU, because Mars is at like 3-ish AU, we actually see some systems that have multiple Jupiter mass planets in those limits. And they're stable, and they're old, so it doesn't seem to be an age-dependent thing necessarily.
Oh, okay, it seems like we have one more question. Right down here.
Okay, so the dish you were showing, this is a very basic question. Are the gas for the planets are, or the planets are resurrected?
So the images that I was showing, we expect that the planet will either eat the mass. Yeah, it'll carve out a gap either by eating the mass or by throwing it out of the gap. So we expect the planets to be forming in the gaps as opposed to the bright rings.